Hello, my name is Ardi and we are going to solve problem 6.28a from Sedra and Smith book. So the question is, for the circuits in figure P6.28, assume that the transistors have very large beta. Some measurements have been made on these circuits with results indicated in the figure. Find the values of other ladder voltages and currents. So in the problem A, we are asked to find out I1 and then P2. Okay, and we have this BJT transistor here. Okay, let's label its node. So this is the base, right? This is the base. And then this is the emitter. So this is E. And then this one here is the collector. Okay, great. And let's make assumption. Assume that the BJT is in the active condition. The BJT is active. Okay. When the BJT is active, we know that VBE is 0.7, right? I mean VEB, right? Because this is an NPN transistor. PNP, I forget that. But here we will have VEB is equal to 0.7. And we know that is valid because this is 0.7 and this is the ground. So the voltage here will be 0. Great. Now, what can we do? First, I think we can find out I1 here using Ohm's law. Why? Because we know the value here in the voltage in the origin and then the voltage in the destination here. So this is 10.7 and this is 0.7. We can calculate the current using Ohm's law, right? Let's do Ohm's law. Let's do Ohm's law. We will have I1 is equal to 10.7 and then minus 0.7, good, and then divided by the resistance between them, which is 10 kilo ohm. So we will have 10 divided by 10, and that is 1. And the unit, because this is volt and this is kilo ohm, we will have this is milliampere. So we get the first value, which is I1 here. So we will have I1 is equal to 1 milliampere. That is good. Now we need to find out P2. But first, I think we can find out the current here. So let's name this as, what is it? IC. And here we will have IB. Okay, IB. Remember that in the transistor, BJT transistor, IC is equal to beta IB. But then, what is IB? IB is IC divided by beta. Okay, remember from the problem, we have very large beta. So we can assume that beta is infinity, right? So what that means that this one is IB is equal to IC divided by infinity, which is just 0. So we will have 0 milliampere here. So here I1 is 1 milliampere. And then IB is 0 milliampere. But then we can calculate IC using KCL, right? So we'll have KCL. KCL at the BJT. Okay, KCL said that the sum of the current that goes in will equal to the current that goes out. Okay, the only current that goes in is I1. Okay. And then there are two currents that goes out, which is IB and IC. So I will have IB plus IC. Okay, let's plug in the value that we have here. I1 is 1. Okay, good. And then IB is 0. And then plus IC. Okay, that means that I will have IC is 1 milliampere. Good. So now we will have IC is equal to 1 milliampere. But we are not asked about IC, but V2. Okay. But then V2 can be calculated using Ohm's law. Okay, I think we have full slide here. Let's erase them first. Okay, now we got this. Let's use Ohm's law to find out V2. Okay, again, so we'll have Ohm's law to find out V2. So we will have V2 minus this value here. So we will have minus 10.7 and then divided by the resistance between them, which is 10 kilo ohm. And all of that will equal to 1 milliampere. 1. Okay, now let's cross multiply. So we'll have V2 minus and minus become plus. So I will have 10.7 and that will equal to. Okay, then what can we do from here? I think we can just, oh, that will be 10, right? 10. And so we will have V2 is equal to 10 minus 10.7, which is V2 is equal to minus 0.7. And the unit will be volt. And I think that's all. This is I1, which is 1 milliampere. And then V2 is minus 0.2. And I think there is nothing wrong with our assumption because this is 0.7 volt. PB is 0. So this is larger than this. And then 0 and this one will be minus 0.7. So 0 and minus 0.7, the current can go here, right? So the assumption is correct in this point. So we have I1 is 1 milliampere and then V2 is minus 0.7. And that's all. Thank you for watching. See you in the next video. Bye bye.